Welcome to this fifth lecture of the 6th week of the course in machine learning. The theme of this week is recurrent neural networks. So looking at our map for this week, you can see where we are. We really, in the last 3 lectures, we looked into feed-forward networks with backpropagation, and actually recurrent neural networks is an area which is clearly within that tradition. And the key point here is that the problem with the networks we looked at up to now not necessarily are very good at handling complex data, sequences, and temporal structures. So recurrent neural network have the ambition to remedy those weaknesses. A recurrent neural network is a class of artificial neural networks which are able to handle sequences or complex data in space and time. This allows RNNs to exhibit temporal dynamic behaviors. So unlike feed-forward neural networks, RNN have a memory, some kind of memory or persistent state that affects forthcoming computations. It should be asserted that many RNN systems implements memory indirectly by unfolding of the network into time step using hidden units. So one can say this is a stateless fashion, and we will come back to that in more detail. Only some RNN has explicit cell states, which we call the stateful fashion. So RNNs can use their internal state, independently of how those are that is implemented, to process temporal sequential structures and varying length of inputs and outputs. This makes them applicable to tasks such as handwriting recognition or speech recognition. So one could say that if we look at the 2 big areas actually today of machine learning, one has to do with language and speech, and one has to do with images. So one can say that RNN really contributes to make this kind of networks efficient in the language and speech domain. While we'll come later, when we look at convolutional networks, we'll say that they target, have the goal to make ANNs efficient in the image analysis domain. Okay, so an RNN performs the same task for every element of a sequence. That's the reason for the name, recurrent. That's very important because if one should treat elements of a sequence differently, that would create a very, very complex machinery. So the elegance here is that you can handle elements in a sequence, but you treat them in a similar manner. So finally, RNNs have cycles, in contrast to ANNs. And it takes both the output of the network from the previous time step as input and uses the internal state from the previous time step as starting point for the current time step. Obviously, we have many different situations where we have more complex input than we have used to be handled in the ANN case. So you can see at the far left of this slide, you can see the really clear one-to-one mapping. So we have well-defined objects, discrete objects, and that map to some output value or some output class. Okay, so then to the right, you can see different, more complex situation. So one situation could be that you have a very complex input object, like an image, which you really, in order to handle that kind of objects, you have to divide it up. You have a single input, but you need some ability to look into that object and divide it up in some fashion. So you can say the second case is you have a complex object and you have to map it on a certain number of values, a certain number of classes. So another case is you explicitly have an explicit sequence as input. Could be a words, and you want to map this sequence of word onto something like an opinion or whatever it could be. A third example is that you have a sequence of input, like in a sentence in language. And so, for example, in machine translation, you can also say this sequence of words should be translated in another sequence of words. So that is another situation. So finally, you have the more complex case. You have many inputs. You have many outputs. Could be happen in, for example, in video analysis and applications like that. RNN has received substantial interest in the neural network world and can also boost many success stories, in particular in the context of applications in language and speech. As a consequence of its popularity, the area has many alternative lines of development that are totally trivial to follow. So it's not so easy always to understand the limits of this sub-area. Therefore, we will start to discuss what we call a vanilla RNN, a single-layered RNN that can be unrolled and replaced with a strictly feed-watered acyclic neural network. A requirement for the vanilla is that time can be discretized, which in turn requires that the duration effect of single neuron activities are finite, also called finite impulse recurrent network. So a network that lacks this property is called infinite. But obviously, we will focus on the finite type. So after looking into vanilla RNN, we will look at two natural extensions of that. So one extension is to allow dependencies not only backward in time but also forward. The vanilla RNN enables us to, at a later stage, to look back at earlier states, or actually at earlier elements of the sequence we study. But we could also introduce mechanisms that we could look forward in time. So that's what you do in the bidirectional case. But we can also stack RNNs, having multi-layer systems. And one reason for that is that if we look at an application like in language, we have letters, and letters for a word is a sequence of letters. But you can have a sentence which is a sequence of words, and then we can say you have a paragraph that is a sequence of sentences. So actually, when you got a long sequence of language input, you don't only want to look at sequence on one level, you may want to look at all these sequences on various levels of abstraction. So therefore, one can think of that you have one RNN unit, a neuron, on each of these levels. And obviously the layers can be individually unfolded as for the single layer case. So necessarily these two extensions doesn't destroy the nice property of the vanilla RNN that it can be unfolded into a strictly feed forward. Furthermore, the RNNs does not solve, the vanilla ones does not solve, but rather makes problems like vanishing gradient or exploding gradient even worse. Vanilla RNNs in practice also a problem to handle very long sequences. Of course, many times due to that long sequences create very deep networks, and deep networks get all these problems. So we will look into one attempt to handle these problems called short long-term memory, SLTM, which introduces a more complex machinery in each neuron. Essentially by having the purpose of getting better control of the signal processing in and among the units. So finally, what is worth mentioning is that there are some architectures that are classified as RNNs. but are not able to handle dynamically handle input sequences. However, these systems have cycles and they have internal memory, so that's the reason for including them. An example of such is an associative memory architecture like a hop-field network that we also will discuss separately later. Let's now look into what it means to unfold a vanilla RNN. So we consider the case we have multiple time steps of input, multiple time steps of internal state, and multiple time steps of outputs, which actually happens when we need to be there when we handle a sequence. So we can unfold the original RNN, which has a cycle, into a graph without any cycles. So this means that we in a way duplicate, we create copies of the RNN unit where the cycle is removed. So the output from the first instance goes into the second, the input from the second goes into the third, and so on. And eventually output in each stage then of course could be fed upwards from any of the states to other network structures. So we can see that the output Y and internal state U from the previous step are passed on to the network as input for processing in the next time step. So bias is also, of course, is still there. I mean, the bias is thing inherited from the general concept of neural network, but we will disconsider that for the moment because it would just block the sight. So a key thing here is that the network does not change between the unfolded time step. The same weights are used for each time step, but it's only the outputs and internal states that differ. So exactly what we do is replicate the exact structure without modifications. One can also remodel, so as you see in the middle here, the most natural thing is to view this on the same level, but then you make copies for each instance of the sequence or instance in time. But one can also reshape that, so graphically one could say that what this does is that this adds to the depth of the network, so that the copies instead are layered in a horizontal way or are layered in a vertical way. But this is just different ways of depicting it. The important thing here is that by this transformation, if it's done in a correct way, ensures that the result of the unfolding becomes just a normal feed-forward network. Of course, by unfolding n times, if we have a long sequence, we create a very deep feed-forward network. One layer for each input sequence. On this slide, you can simply see another example how the unfolding can look like. But you get input for every instance. You get output from every instance, but you also feed the internal state from instance to instance. The consequence of unfolding for the learning process is as follows. So if you carefully do what we described in the last slide, and you actually get a straightforward feed-forward network, it's potentially possible to still update the weights. That means to learn through backpropagation. So the backpropagation of error of a given time depends on the activation of the network at the prior time. So error can be propagated back to the first input time step of the sequence, so that error gradient can be calculated, the weights of the network can be input. So with only marginal modifications, we can talk about then backpropagation through time. And it doesn't matter whether we backpropagate through the normal layers of the network or we backpropagate through those unrolled levels of the RNN. I mean, of course, there are subtleties here. So for recurrent NPTEL, the loss function depends on the activation of the hidden layer, not only through its influence on the output layer, but also through its influence on the hidden layer at the next steps. So small complications, but more or less the same procedures can be applied. The most natural extension of the vanilla RNN is to introduce many levels of RNN or stacked RNN. Obviously, each layer in the stack can be individually unfolded, as for the single layer case. The main reason for having many layers is that the layers correspond to different levels of abstraction or aggregation for the sequential and temporal data items. As an example, in word processing, the first layer can model sequences of characters, the second level sequences of words, the third level sequences of sentences, etc. The risk by increasing the number of layers, of course, is to make problems like vanishing gradient even worse. But we still, because we unfold, as you see, I mean, every layer is still considered to be possible to unfold. So this means that the resulting structure is still then a conventional feed-forward network, but with some of its problems increased, of course. The next extension is what is called bidirectional recurrent neural networks. So by introduction of that, the output layer can get information from past and future states simultaneously. That means both backwards and forward links are enabled. So the principle in realizing that is to split the neurons of a regular RNN in two directions, one for positive time direction for states and another for negative time direction. So one can view this as a second step of unfolding. So you have the normal unfolding to handle the sequences, but in order to being able to look both forward and backward, for every already unfolded sequence, you duplicate that with one copy for the forward direction and the other for the backward direction. So, and actually, these two hidden layers can both be connected to the same output, and they are independent of each other. So it doesn't mean that the one direction feeds something into the other. So they can be treated separately and be used to give information to later levels, one by one. Of course, a natural extension now is to combine the stacking of RNN with the bidirectional model. So nothing prevents that even bidirectional recurrent networks can be stacked. So obviously, to sum up, we are still working with a scenario here where everything we talked about can be unfolded, and the net result of everything we have done will still be a feed-forward network, which has a certain beauty about it. So let's now go back a little and look at some of the challenges for neural networks, feed-forward ones, and in particular also for RNN. So there are three kinds of problems. The vanishing gradient problem, we have talked about that already, and the problem there, as we already said, is that the gradients become too small. And the reason for becoming so small is that the individual derivatives or gradients are combined using the chain rule, and the chain rule is applied one time in every step. So if you have many steps, and you start with a gradient in the range of 0.1, very rapidly they approach 0. And the effect of that is that the update of weights are stuck. The opposite problem is that you can also get very large error gradients. And this kind of large updates then have the effect that the network can become very unstable. So There are ways of handling that too, and in many cases it's many times more difficult to defend oneself against the vanishing radius problem. Also, one issue is the very long sequences and temporal dependencies. Of course, they are not a direct problem, but they indirectly create a problem. In particular, invoke problems of vanishing gradient because they create very deep networks. And these very deep networks are then hampered by the other mentioned performance problems. Long short-term memory networks, LSTM, are extensions of recurrent neural networks, which basically extends their memory function. The core of the approach is to elaborate the interior of a vanilla RNN unit with the purpose to increase control of signal flows. LSTM was explicitly designed to combat the vanishing and long-term dependency problems. LSTM was introduced by Hochreiter and Schmidhuber in 1997, and the units of an LSTM are used as building blocks for the layers of an RNN, which is then often as a whole called an LSTM network. So LSTMs enable RNNs to remember their inputs over a long period of time. This is because LSTM contains their information in a memory that is much like the memory of a computer, general computer, because the LSTM can read, write, delete information from its memory. LSTMs are widely recognized academically as well as commercially, extensively used for speech and language processing by companies like Google, Apple, Microsoft, and Amazon. So hopefully this slide explains the difference between an RNN vanilla unit and an LSTM unit. So actually you can see that apart from the normal signal processing functionality of the RNN neuron, the LSTM neuron has a much more complicated interior. And essentially, the difference is that the LSTM unit, apart from anything else, has some gating functionality that controls the signal flow. So the LSTM memory can be seen as a gated cell, where gated means that the cell decides whether or not to store or delete information, typically by opening the gates or not, based on the importance it assigns to the information at hand. The assigning of importance happens through weights, which are also learned by the algorithm. This simply means that it learns over time which information is important and which is not. Specific to LSTM is the cell state manifested by the horizontal line running through the top of the diagram of the unit. This is this is manifested by the different C's for cell state. Also in an LSTM unit you have 3 gates. These gates determine whether or not to let new input in, the input gate, delete the information because it isn't important, forget gate, or to let it impact the output at the current step, output gate. So that's the basic functionality of this kind of unit. So some comments on structural aspects of LSTM. So in principle, LSTMs can, as for vanilla RNNs, be unfolded, be stacked in a multi-layer structure, be arranged in a bidirectional fashion. All these are possible. If this is done in a stateless fashion, that no cell state is used, that explicitly the state information just flows across, then the resulting network is a normal feed-forward network, potentially with deprivation. However, if the LSTM cells use explicit cell state, stateful fashion, it becomes more classified, and there is no guarantee that exactly this feed-forward network mechanisms can be used as in the default state. But nothing prevents to combine these elements in more complex structures as envisioned here. So what we have done in this lecture is to look into some of the more important aspects of RNN. So we looked at we call the vanilla type, the full or standard RNN that can be unfolded. We also have talked about how that can be extended with multiple layers, with bidirectional links, and we then also showed one approach, a well-known approach, how the signal processing can be improved in the LSTM case. There are so many different variables in this area that, and below in this slide you can see a few of them. Many networks that are classified as RNNs, and there are so many approaches. More or less these different approaches relates to the simple ones. So for example, a gated recurrent unit, GRU, is a simple version of LSTM. Elman networks are very early, kind of standard RNNs with rather simple structures. Optical networks will be described in another context of associative memory, and so on. But it's outside the scope of this lecture to go in more details of all these, I would say, jungle of different approaches developed. So this was the end of this lecture. Thanks for your attention. The next lecture, 6.6, will be on the topic Hebbian learning and associative memory. Thank you.